The extension is here only in NMR. Other things are there anyway. So we'll start from UV visible spectroscopy. Some basic concept, that is various electronic transitions, Beer-Lambert's law, effect of solvent on electronic transition, ultraviolet spectra of carbonyl compounds and unsaturated carbonyl compounds. That means conjugation. Conjugated system and non-conjugated system or containing pi bond, all these things. Then some illustrative example, spectra of dienes, conjugated polyenes, then Fisher-Woodward rule, all these things. Uh, anyway, do you have the study material? Let me ask.
Sir, as of
For
now, right
this,
now, I'm not having. I have to downloading.
is it uploaded in the site?
No, sir.
No,
Yes or no? What
no,
I
no,
tell you?
no,
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 sir.
No.
no.
So that's why I'm asking. Is it not uploaded so that I cannot down? I could not download. So anyway, this there are so many books. I think in your degree, what book you are referring? What book you have referred for spectroscopy? If you can see the reference here for further reading, you have the Pavia, Introduction to Spectroscopy, and Silverstein also there. So these are
Sir,
the good
could
books.
you please share these things with us? Means
Which one?
through
Which
through
one?
WhatsApp, these references.
It is there. I am what I am showing, that is the syllabus only. The
Okay,
syllabus page I am just showing in the screen.
okay.
So whatever books are here for reference books, you can see.
Mm.
So and the best book for you will be the Y.R. Sharma, Organic Spectroscopy by Y.R. Sharma. I think you have gone through that one in your plus 3 or degree classes. Anyway, so that I am showing this one. This is the book, Elementary Organic Spectroscopy for BSc Honors and Postgraduate students, Y.R. Sharma. This you can download, it is there, and other books are also there, you can download. Till it is not uploaded in IGNOU website. Okay.
Okay. So it can be downloaded normally if we put in search, it will come. This one.
Yes, yes,
Where?
this one it will come. I have downloaded this one only. If there is any
Okay.
difficulty, then you just tell me. I will share it with you.
Sir, may we have your contact number? Which would
You
be
can
what?
note it.
Yeah.
It was in the group. You are not in that group.
Which group, sir?
I don't know. Okay, you could just write 8249 666
8249 666
843.
843. 8249 666 843.
Yeah.
Okay, sir. Thank you, sir.
Okay, so we'll start.
Sure.
Spectroscopy, as the syllabus tells about the spectroscopy of organic compounds, spectroscopy identification of organic compounds. So we'll start. First part is the introduction part, and as you have seen here, we have UV visible, IR, NMR, and mass. Four
Okay.
spectroscopy methods are there. So we have 4 classes, 4 days we have. So today we'll try to finish UV visible and some introduction part. IR is
Yes, sir.
okay. So this
Yes.
NMR, it will take little time. Tell.
Sir, Saturday also classes will be there.
No, it's not there. It is Wednesday, Thursday, Friday, and then Tuesday, I think,
Monday.
21st.
Acha,
Tuesday.
Tuesday. Okay. Okay, sir.
So 15, 16, 17, and 21. Okay. So spectroscopy, and we know all these things. The introduction part: what is electromagnetic radiation? What are the different components of electromagnetic radiation? That is wavelength, wave number, frequency. Okay, and we'll not discuss that one. And total electromagnetic spectrum, which started from the gamma ray to radio wave. Yes, yes. So total electromagnetic spectrum starting from gamma ray to radio wave. This is in the increasing order of wavelength. So what is spectrum? Spectrum, the arrangement of all types of electromagnetic radiation in order of their increasing wavelength or decreasing frequency is known as the electromagnetic spectrum. Reverse, because wavelength and frequency, they are inversely proportional. So if wavelength increases, then frequency decreases. So either in the increasing order of wavelength or frequency, whatever may be. So in orderly, if you arrange total the range of electromagnetic radiation, so what we will get, that is electromagnetic spectrum. So with lower wavelength, we have gamma ray, then still higher, which is having 1 angstrom dimension, that is X-ray, then ultraviolet. Ultraviolet radiation, if you consider, it starts from 190 nanometer and till up to 400 nanometer. 190 or nearly 200 to 400 nanometer is your ultraviolet region. Then from 400 to uh, 800 nanometer or 4000 to 8000, that is your visible spectrum. As you know, it starts from violet, ends at red, violet, indigo, then green, sorry, blue, then green, then yellow, orange, and red. Visual. So that is the visible range, visible light. So the difference between radiation and light, you must know. The radiation which gives you the sensation of vision is known as light. So visible radiation is known as visible light. Others are radiation, because we can't see other electromagnetic rays or radiation. We can visualize only the visible range, so it is visible light. Then infrared, which is above 800 nanometer or 8000 angstrom. So if you consider the wavelength, it is between 10 to the power minus 6 to 10 to the power minus 4 meter. So it is infrared. Then microwave, so then radio wave, the radar wave, or this is frequency modulated, TV wave, short wave, AM, like that. But after infrared, you have microwave, then radio wave. So this is the complete spectrum. Now, what happens if light or electromagnetic radiation pass through a medium or a substance? So, as we know, the electromagnetic radiation, according to Planck's quantum theory, energy can emitted or absorbed by a substance in the form of, it is absorbed discontinuously in the form of small packets, or those packets are known as quantum, plural is quanta, and in case of light we are telling as photon. So according to Planck's quantum theory, when a radiation is observed, it will absorb or emit in the form of quantum, in form of small packets. That means either it will absorb one quantum or two quantum, three quanta, like four quanta, like this. So a fraction of quanta, a quantum, is cannot be emitted or absorbed. Am I clear? Can you understand me or not? This is the
Yes, sir.
basic preliminary things. So when light will be observed by a certain substance, then what will happen or what change will happen in that substance? So first thing, if you consider starting from gamma ray or X-ray, they're having lower wavelength, means they have high frequency, and according to Planck's quantum theory as E equal to h nu. So if frequency will be more, then energy will be more. That means gamma ray, X-ray, they're having higher energy. So energy decreases if you move from left to right of the spectrum, as we have seen here. What?
Sir,
So
no
we
more
will now
visible
deal.
the screen. Pardon, sir.
Pardon?
Screen is not
Pardon?
screen is
Not
not
visible.
visible. Yes, sir.
What happened? Initially it was visible, na?
Yes, sir.
Yes or no? Now is it
Yes,
visible?
it was visible. It got
Huh?
means vanished now.
Stuck. Okay, I'm sharing again. Is it okay?
Yes, sir.
Is visible now?
Yes, sir.
Okay. So this total electromagnetic spectrum what we have I have presented here, that is in the increasing order of energy. Sorry, decreasing order of energy. With gamma ray and X-ray, they will have higher energy than UV, then visible infrared like this. So, as so far as our syllabus is concerned, we have only UV visible and IR. Ultraviolet visible, that is in one chapter, UV visible, and then infrared. Then that NMR, nuclear magnetic resonance, that we have that radio wave. In the radio wave region, some resonance will occur that we will discuss. But mass is different. So in electromagnetic radiation, so let us consider this UV visible and infrared, these things. So when an, a compound is irradiated with ultraviolet ray or visible ray, they are having higher energy in comparison to infrared. So when energy will be absorbed, according to Bohr's, I've seen the atomic model for hydrogen atom. So when energy is absorbed, electron jumps from lower energy level to higher energy level in an atom. But here we have supplying the electromagnetic radiation to a molecule. So therefore, the in as ultraviolet rays they are having higher energy. So this energy, when absorbed by a molecule, there will be electronic transition. So when electronic transition will be there, that means electron will move from lower energy level to higher energy level. We'll discuss that on where is the energy level. That means from which energy level it will transfer to which energy level. So there will be electronic transition. So electron will move from lower to higher energy level. So when at higher energy level it is unstable, then it will come down to the lower energy level by emitting the same radiation of same amount of energy, and that will be appear as the spectrum, and that is known as UV visible spectrum. So, in a molecule, we have, according to molecular orbital concept, we have bonding molecular orbital and anti-bonding molecular orbital. Am I clear? Any molecule which is formed by combination of constituent atoms combine to form molecule. So the atomic orbitals they also combine to form molecular orbital, and number of atomic orbitals combined will be equal to the number of molecular orbital. That means two atomic orbital, when they will combine, you will get two molecular orbitals. One will have lower energy and the other will have higher energy in comparison to the corresponding atomic orbital. So the molecular orbital which will have lower energy is known as the bonding molecular orbital, and which will have higher energy is antibonding molecular orbital. So, in a molecule, electronic transition occurs from the bonding molecular orbital to the antibonding molecular orbital. So, therefore, when molecule will absorb energy which is in the range of infrared or visible radiation, then there will be electronic transition from bonding molecular orbital to antibonding molecular orbital. So that is the concept of ultraviolet and visible spectroscopy. So we know we have the sigma and pi bonding molecular orbital and also antibonding. Here n represents the non-bonding molecular orbitals, as you can see here, sigma, pi, and n. So this technique, spectroscopy, is also known as electronic spectroscopy because it involves the promotion of electron from sigma, pi, or n. N is the non-bonding electrons from the ground state to the higher energy state. So that means there will be transition from sigma bonding to sigma antibonding or pi bonding to pi antibonding, that is known as sigma sigma star transition, pi pi star transition, and n sigma star or n pi star transition, because n is the non-bonding molecular orbital which don't have any antibonding molecular orbital. So n is the non-bonding, so it will have only one orbital. But sigma type, sigma bonding and sigma anti-bonding will be there. So sigma, sigma star, pi, pi star, and n. From n, transition occurs to either n to sigma star or n to pi star. That we'll discuss in detail. So this spectroscopy, it is applicable to, as you have seen here, to alpha beta unsaturated carbonyl compounds or homoannular or heteroannular compounds, and it occurs between 200 to 800 nanometer or micrometer, same thing, nanometer and micrometer. Okay, and there are some problems, these things you know how to convert. E equal to h nu, what will the energy? If frequency is this much, what is the energy? So simple calculation, by putting E equal to h nu you can find out. Then here we have two laws, the absorption laws, the Lambert law and Beer's law. So Lambert's law, the statement is, when a beam of monochromatic radiation passes through a homogeneous absorbing medium, the rate of decrease of intensity of radiation with thickness of absorbing medium is proportional to the intensity of incident radiation. This you are facing in your day-to-day life. For example, you have taken a blue cellophane sheet, or you can say blue glass or blue transparent sheet, whatever, blue or green, whatever may be color. So if it is a single sheet, what you can visualize, you just hold it on your eyes and you can visualize the other part. So when two sheets will be joined, okay, then the vision, it will decrease, the intensity will decrease. That's the thing. So that means if thickness of the sheet, it will go on increasing, then intensity of light which will pass, that will decrease. So that's why the Lambert's law, same thing. That means when a beam of monochromatic radiation passes through a homogeneous absorbing medium, it is not solution. Okay, so generally students confuse here between Lambert's law and Beer's law. Beer's law tells about the solution, but Lambert's law is the absorbing medium, not the solution. For example, a glass slab, colored glass slab, or the cellophane sheet, what I told. So that is a homogeneous medium, absorbing medium. So when a beam of monochromatic light passes through a homogeneous absorbing medium, the rate of decrease of intensity with thickness, if intensity is I, so di by dx, rate decreases, so minus di by dx is proportional to the intensity of incident radiation. That is, it's proportional to I or equal to Ki. K is the proportionality constant, okay, which is also known as the absorption coefficient. So I is the intensity, x is the change in thickness. So di is the infinitesimally small decrease in intensity of radiation on passing through infinitesimally small thickness dx of the medium. So minus di by dx, that will be equal to ki, or just rearrange it, di by minus di by I equal to minus k dx, then integrating from I naught to I naught is the incident radiation, I is the radiation at that particular thickness x. So here the limit will be x equal to 0 to x equal to x. So finally we will get ln I by I naught will be equal to minus kx, or I by I naught equal to e to the power minus kx, or I equal to I naught into e to the power minus kx. Okay. Now, what is the intensity of radiation observed? So I observed, that will be equal to I naught minus I, incident intensity of incident radiation, and I is the intensity after certain distance, passing through certain distance. So observance or intensity observed, that will be equal to I naught minus I, which is equal to I naught into 1 minus e to the power minus kx, same thing. So if you convert it to base 10, then I will be equal to I naught into 10 to the power minus ax. So where k we have to convert to a, because ln and log difference is 2.303 log equal to ln, that you know. This is 10. So that's why a will be equal to k by 2.303. So a is known as the extension coefficient of the observing medium. When we are using the natural, this base 10 natural logarithm, when we are converting to base 10, then this a, which is equal to k by 2.303, is known as the extension coefficient. So this is the Lambert's law. Then about Beer's law. So this law states that when a beam of monochromatic radiation is passed through a solution, okay, solution means we have two variants here, the thickness and also the concentration. Okay, thickness is there, concentration is also there. So when it passes through a homogeneous solution, then the rate of decrease of intensity of radiation with thickness of the observing solution is proportional to the intensity of incident radiation as well as the concentration. There was only intensity, here intensity and concentration also, and the concentration is expressed in moles per liter. So similarly, if you go on integrating with the same limit, same thing. So here we have taken the constant as k dash, there we have taken k. So to differentiate, we have taken k dash. So finally, we will get I equal to I naught into e to the power minus k dash cx converted to base 10. So I equal to I naught 10 to the power minus a dash by cx. So where a dash equal to k dash by 2.303. So this is known as the molar extinction coefficient. There it was only extinction coefficient, and here we are using molar extinction coefficient. Why? Because concentration we are expressing in moles per liter. So this is molar extinction coefficient. So you can see then we can state the Beer's law again, that when a monochromatic light is passed through a solution of an observing substance, its absorption remains constant when concentration and thickness of the absorption layer are changed in the inverse ratio. Because C, you can see C and X, if they will change in inverse ratio, that means if C increases proportionately, X decreases, then the absorption, okay, the absorption, it will remain constant. So now we will combine these two laws. So on combining two laws, we know the it's known as Beer-Lambert law. So you can see here. So log, go to this one. So log I naught by I, or log I by I naught equal to minus a prime cx. So if you take it log I naught by I, so it will be equal to a dash cx. So this a dash we have converted to epsilon. So epsilon nothing, the same thing, the molar extinction coefficient. What was there in a dash we have changed to epsilon. C is there, and x The thickness we have converted to L. Same notation, same representation, but different notation only. So I naught is the intensity of incident light, I is the intensity of transmitted light, C is the concentration in moles per liter, L is the path length of the sample or thickness, which is usually 1 centimeter. When you are using the UV spectroscopy, this is the cuvette. Inside the cuvette, we'll put the sample, maybe in the solution form, then we'll pass the UV visible radiation. So this X is the thickness of the sheet, or it is the thickness or path length of the sample, up to what path it will travel. So path length, that is L, which is usually 1 centimeter, because this cubette has having dimension 1 centimeter length and 1 centimeter breadth, and height is about 4 to 5 centimeter. So we are not bothered about the height, only this length we know. This is 1 centimeter, this is also 1 centimeter. Okay, and epsilon is the molar extension coefficient or molar absorptivity, and that is equal to the observance. So observance will be equal to logarithm of incident radiation or ratio of incident radiation to radiation at a particular concentration or thickness. Clear? So A equal to log I naught by I, or which is equal to also epsilon CL. About the limitation, this law is not obeyed when different forms of observing molecules are in equilibrium, as in keto-enol tautomer. The keto form and enol form, as you know, in case of acetone and vinyl alcohol is the enol form, CH2 double bond CHOH, vinyl alcohol, and acetaldehyde is CH3CHO. So acetaldehyde and vinyl alcohol, they are tautomers or keto-enol. So this law is not applicable. Why? Because keto and enol form are in equilibrium. The tautomerism says about the two forms are in dynamic equilibrium with each other. So at where the keto form will observe, the enol form will observe in the different wavelength. So then the observance there will change. So it will not depend upon the concentration. It depends, but the concentration we cannot measure. For example, if you are taking like vinyl alcohol, so whether how much of the sample is vinyl alcohol and how much percentage is your acetaldehyde, that is difficult to find out. Then how will find out the thickness or concentration? So it is not applicable. And when fluorescent compounds are present, because fluorescent compounds, they will emit light by themselves only. So how much they will absorb, that is different, or how much they will emit, whether they are emitting the rest which have been absorbed from you, that electromagnetic radiation, or they are emitting their own because they are fluorescent. So we cannot apply. And when solute and solvent form complex through some sort of association, solute and solvent, they form complex. If you are taking water, generally water forms complex with copper. For example, you want to find out the spectra of anhydrous copper sulfate, which is white in color or colorless. But when it dissolves in water, it will form complex with copper sulfate, forming tetra aqua, or sorry, penta aqua copper sulfate, which is blue in color. Then absorbance will change. So if it will form complex, then color will, this is one example. You can just visualize that one. Anhydrous copper sulfate. That means if anhydrous copper sulfate, you will dissolve any other anhydrous polar solvent, it will not give blue color. It will be colorless. But when you are dissolving water, it will give blue color. So that is due to the formation of complex. Then this law is not applicable. So these are the two laws which govern the UV visible spectroscopy. Then there are some problems that you can go through. Then we'll move to the different types of electronic transition. Selection rule, okay, and here, because selection rule, you should know the symmetry. That means the shape of sigma molecular orbital, sigma antibonding molecular orbital, pi bonding and pi antibonding molecular orbital. So selection rule tells that the transition which involves a change in spin quantum number of an electron during the transition do not occur. If there will be a change in spin quantum number, that means the singlet triplet transition are forbidden. Okay, that means for example, two electrons are there in the same orbital. If two electrons, because any orbital that can accommodate maximum two, and these two electrons will be in opposite spin. If one will be plus half, the spin of other electron will be minus half. So in that case, we are telling it is in singlet state because 2s plus 1. Either it is, you see, 2s means half plus half, okay, or half plus 1. So it will be in, and yes, means plus half and minus half, it will cancel. So 2 into plus half plus minus half, that means it is 0. 2 into 0 plus 1. So it is singlet state. And if both will have same spin, that means half plus half plus half. So plus half will be 1. So 2 into 1 equal to 2 plus 1 equal to 3. So it is triplet state. That is the formula 2 into S, 2s plus 1, where S is the spin quantum number. So spin, if they will be in opposite spin, then one will be plus half, other will be minus half. So summation will be 0. So 2 into 0 plus 1, so it is 1. If both will have same spin, either plus half or minus half, so whatever may be. Don't confuse that minus half and minus half will be equal to minus 1. So 2 into minus 1 equal to minus 2 plus 1, then it will be minus 1, not like that way. So if it is plus 1, same spin means we have to consider half half. Plus and minus that represents the direction of spin, whether it is clockwise or anti-clockwise. So half half will be 1. So 2 into 1 equal to 2 plus 1 means 3. So it is in triplet state. So that means if two electrons are in the same orbital, they will have opposite spin. When it will move to the higher orbital, one electron will jump to the higher orbital with the same spin, it should move up. There will be no inversion of spin. If it is anticlockwise, it will remain as anticlockwise. Then only that transition will be allowed. Otherwise, if they will have same spin, it is forbidden. So singlet triplet transitions are forbidden. This is one. Second, the transition between orbitals of different symmetry do not occur. For example, n pi star transition is symmetry forbidden because one is garret, pi star is symmetrical and n is unsymmetrical. So unsymmetrical to symmetrical transition is forbidden. Forbidden in the sense, in such case, whatever observance will be there, the intensity will be very low. Forbidden means we cannot rule out completely. Transition will be there, but intensity or epsilon max, that is the epsilon max is the maximum intensity, this is lambda max, and what is the maximum absorption, that is known as the epsilon max. And lambda max is where the peak will occur, that wavelength is known as lambda max. Wavelength of maximum absorption is lambda max, and the observance is known as the epsilon max. So generally the observance you can see, it may be noted that intensity of observation is directly proportional to transition probability, and allowed transition will have epsilon max value greater than 1000. So if it will be more than this observance, or if epsilon max, if it will be more than 1000, then it is a allowed transition. Those having low transition probability will have its value less than 1000. Okay, so that is the thing. Then go for instrumentation. In instrumentation, we have, can see the source of light, prism, that is a monochromator, converts, or it will only slits are there. It will only one wavelength will pass. Then there is a prism will split into two halves, one for the sample, one for the reference, okay, reference beam, one is the sample beam. Then the photo cell, that means sample will be placed. Then we come here, the electronic amplifier, because why we are taking the reference beam? So here we'll take the solvent only. In one is solution, one is the solvent. So observance due to solvent,
Pardon, sir.
we
Pardon,
subtract.
sir.
Yes, yes.
Sir, reference as reference, what kind of solution we'll be using as a
See,
reference usually?
whatever solvent you are taking for making the solution of the sample, whatever
Yes.
solvent, you may take
Okay.
water, you may take alcohol, in which the substance is soluble, you have to take the solution.
The
And that
respective solvent.
solvent, that solvent you have to take as the reference. Because we have to
Okay.
subtract, because solvent will also absorb some
Yeah.
radiation. So we have to subtract that one, then we'll get the peak here. That is, that peak will be, or the spectrum is for the sample only. Okay, this electronic amplifier, then there will be some subtraction type of thing. Then the pen is nothing but today nowadays we are using the computer. Earlier it was a pen and paper. Paper will be at the drum, so it will rotate, and pen will be just give the mark like this. But today, nowadays we have very advanced spectroscopy. So in computer we are taking the printout directly. That's why it was not time taking. Earlier it was very cumbersome, very time taking, maybe 1 hour, more than 1 hour for one single spectra. Anyway, nowadays 2 second or 3 second we'll get the spectra. Anyway, so details about the instrumentation you can go through this one. Yes, yes. Why there will be absorption band? It's a very important thing we have
Sir,
to just
I have
imagine.
another query. May I ask, sir? Uh,
Yes, tell.
Sir, currently you are teaching in which place? IGNOU only.
No, no, I am engaged in OUTR, Bhubaneswar,
Acha,
Odisha
acha,
University of Technology and Research.
acha. Sir, all these instruments are over there.
Yes, these things are here. Only.
Okay, sir. Okay, sir.
All the
Okay,
instruments are here. Okay.
okay.
So, have you ever of this band, this type of curve here? I just want to ask, what does it represent? Is it in here energy curve, energy curve for a diatomic molecule? The figure it is showing there. This type of curve you have been taught in case of formation of hydrogen molecule using valence bond theory, molecular orbital theory, valence bond theory in your higher secondary or degree, whatever maybe. That means when two atoms, for example, hydrogen atoms, they will come closer to each other from infinite distance, their energy will decrease because there develops a force of attraction. If force of attraction will be there, then energy will decrease. If force of repulsion will be there, potential energy will be increased. That is the general principle. Attractive force decreases the energy, repulsive force increases the energy. Energy in chemistry, we generally energy when we are telling it is potential energy, not kinetic. So consider this one. So let simple two hydrogen atoms I am telling from infinite distance when they are coming closer to each other, the attractive force develops because each nuclei will attract the other electron. Why is this? So, and there is also repulsive force because two electrons they will repel each other and two nuclei also they will repel each other. Two hydrogen atoms, just imagine they are coming from infinite distance and closer to each other. So that means when the net force is attractive, the bond will be formed. So this is the distance, minimum distance, this one, which is known as also the bond length. Here the bond will be formed or the molecule will be formed. If you decrease the distance further, this is the energy. Here in y-axis we have taken energy, and in x-axis we have the internuclear distance. So this distance is the minimum distance, so bond will be formed. And if you decrease the distance further, then net force will be repulsive, energy will increase. So this is the energy level diagram for a diatomic molecule. Now, energy level diagram means here the electron they will overlap, the orbital will overlap or the covalent bond will be formed. So this is the bonding molecular orbital, okay, of one diatomic molecule. Now, just imagine the diatomic molecule or higher elements, not hydrogen. All elements they will have, when they will form compound or diatomic molecule, they will have the similar type of energy level diagram. So this is the electronic level. That's why we have represented as E1, for example. And in such there is also another electronic level, let it be E2. It can be represented, though it is the shape is different, because bond, this is in case of molecular orbital theory. If this is the bonding molecular orbital, energy level diagram of bonding molecular orbital, then anti-bonding molecular orbital diagram will be like this, what cursor I am showing, the shape, just like this. Okay, not like this what we have shown here. Got the point? Antibonding molecular orbital will be like this, because antibonding molecular orbital, when electron will be there in antibonding molecular orbital, that is counted for instability. So in antibonding molecular orbital, we will not get this well, this type of thing. This is because the well is for what? This is having lower energy, so maximum stability. But in antibonding, electrons are unstable. So it will be like this. But to represent, we have taken the similar type of two electronic level. This is electronic level, not bonding and anti-bonding molecular orbital. This is one electronic level, this is another electronic level. That means electron will jump from this energy level to that energy level. And you can see here something is mentioned here, V1, V2 and V3, that is the vibrational energy level, and each vibrational energy level is associated with some rotational energy level, R1, R2 and R3, R4, like this. Now just imagine an electron, it it will have translational everything, every molecule or every gaseous particle constituent whatever thing, it will have some translational motion, rotational motion and vibrational motion. Any substance, any particle, these three types of motion will be there. Translational, that means linear motion in any direction, x, y or z axis. Vibrational motion, it will vibrate or oscillate through a mean position. Clear? I think you are clear about this. It will vibrate. And rotation, it will rotate around its own axis. So three types of motion: translational, from one point to another; vibrational, through the mean position it will vibrate or it will oscillate; and rotational, it will rotate around its own axis. Can you tell which motion requires more energy? With translational motion requires more energy, or vibrational or rotational? Are you hearing?
Yes, sir. I think rotational.
How? You rotate around about you and you vibrate. Would you follow what I am telling? Vibrate.
The vibrate means molecule is not moving. It is at the same place and
Yes,
it is and rotation
it is
means
just
continuously it is changing its direction, and translation if you
it will
consider, then
no.
translated is yes sir.
Tell.
And
Translatory motion means from one point to another you have to move.
yes, and
For example, you are
rot
going to market. You are going to market. That is translational motion.
yeah, and
And
rotation means
vibration means
continuously it is rotating.
rotating means about your own axis you
Yes,
have to rotate.
yes. So that is
About
why
you
I think
your axis you have to rotate.
yes sir.
No, translational motion will require higher, more energy. If you are moving
Pardon, sir?
one position to another position, if you are moving from one position to another position, one point to another, more
Hmm.
energy will be lost there, or you require more energy for translatory motion. Just imagine from lower energy level to higher energy level. That means you are
Sir,
moving from ground level to
if I'm
hmm,
considering vibratory and translatory, translatory will have
hmm,
requires more energy. But when
yes,
I think when I'm considering rotatory and translatory,
hmm,
I think rotation will take because it is rotating also and along the own axis. So and
yes,
changing the
only
direction
about
also. Yes,
no,
sir.
only you just see you are rotating yourself and you are moving from ground floor to first floor. So translatory motion requires more energy than
Okay, I
vibratory.
got your
Vibratory
point.
means you
I
have
got your point, sir. Got your point.
yeah, you have to vibrate on your own point position only vibration. And rotation you have to rotate at the same position. So that's why I have seen here electronic transition requires more energy. That means each electronic level is associated with a vibratory level. This V1, V2, and V3, they are the vibrational levels. They are inside the electronic level because they requires less energy. And rotational levels, they are inside the vibrational level because rotational energy is less than vibrational energy. Okay, so this curve represents that each electronic level is associated with some vibratory level or vibrational energy level, and each vibrational energy level is associated with some rotational energy level. Got the point?
Yes, sir.
Now, if we want to change the electron, its level, energy level, that means we have to change the electrons energy level, electronic transition, that means electron will move from this energy level to this energy level e1 to e2. Second, electron will vibrate in this same energy level. It will vibrate, that means its energy will change from v1 to v2 or v1 to v3. That is another possibility. Second, third, it will rotate. It will rotate in the same vibrational level. That means here its rotational energy will change, let from R1 to R2 or R2 to R3 or R1 to R3. So three possibilities. Can you imagine? Either electron will transit from the energy level E1 to E2, that is translational motion, or in the same energy level it will vibrate. That means its vibrational energy level will change. That means it may change from v1 to v2 or v1 to v3 or v2 to v3, whatever may be. Third is its rotational energy level will change in the same vibrational level. Let it is in v1 vibrational level and rotational energy level changes from r1 to r2 or r2 to r3. Okay, three possibilities are there. So as I told, it change in electronic energy level requires more energy than change in vibrational energy level than change in rotational energy level. So when electronic transition occurs, that means electron will jump from E1 to E2. So translatory motion will be there. Simultaneously, its vibrational and rotational energy level will also change. Clear?
Yes, sir.
That's why I told electronic transition, if it changes from one energy level, it was spin. Spin means the rotation again. So spin, if it will change, there will be a change in spin, then that is not allowed. That is forbidden. Now I think you got the clear idea. Let electron will jump or it will transit from E1 to E2, where the rotational energy level changes from let or vibrational energy level changes from V2 let to V3. So it is some just for explanation we have given here. V2 to V3 or V3 to V2 is not possible. Okay, just to show the transition we have it is the mark is given here, but V2 to V2 or V2 to V3 whatever there is a change in vibrational and there is also change in rotational. So, but the energy required from change in vibrational and rotational is very small in comparison to the electronic transition. So, when electronic transition occurs, which is which occurs by absorption of radiation in UV, ultraviolet or visible radiation, visible region of the spectrum, simultaneously the vibrational and rotational energy level also changes, but it is negligible. But when we move for infrared, infrared radiation is having lesser energy. That means in that time, during infrared, absorption of infrared radiation, electronic transition will not occur. Only the vibrational transition or rotational transition will occur. That's why infrared spectroscopy is known as vibrational rotational spectroscopy, whereas UV visible spectroscopy is known as electronic spectroscopy. Am I clear? Are you there or not?
Sir. Yes, sir, we can hear.
Okay. So this is the principle. Then the theory of electronic spectroscopy or types of electronic transition. Already I told this one. We have bonding and anti-bonding molecular orbital. So transition, electronic transition will occur from sigma to sigma star, because where the bonding molecular will be there, the molecule is also associated with the same type of anti-bonding molecular orbital according to molecular orbital theory. Sigma bond will be formed by head-on overlapping. So when sigma two orbitals they will overlap head-on wise, we will get the sigma bonding and also sigma antibonding. And if you recall the energy level diagram of hydrogen molecule, lithium molecule, like that, nitrogen molecule, oxygen molecule, we have seen, I think, sigma bonding and this is the energy level. Sigma first, then pi, then if non-bonding will be there, that will be in between, then pi star, that means pi antibonding will have higher energy and sigma antibonding will have still higher energy. So difference between sigma bonding and sigma antibonding is very high. Then n, that means non-bonding and sigma star, pi star, then n pi star. So this is the difference of energy. Very high energy is required for sigma star transition. Then still lesser is n sigma star, then pi star, and n pi star. Now that means if higher the compound, the molecule which will have only sigma bond, there is no pi bond, or n means there is no lone pair of electrons. You follow? For example, if you take alkane, only carbon, 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 hydrogen, sigma bonds are there in case of alkane. So as sigma bonds are there in case of alkane, so when alkane will absorb UV visible radiation, what type of transition will occur? Sigma sigma star. No other molecular orbitals are there. So as sigma sigma star transition requires higher energy, so higher energy means lower wavelength, higher energy means higher frequency and lower wavelength. So it will absorb at lower wavelength or in ultraviolet region. Ultraviolet region will have higher energy. And when the compound which will have only sigma bond and any element which contain lone pair of electron, like let alcohol. Okay, methyl alcohol, ethyl alcohol, what will have, which will have lone pair of electrons over oxygen atom. So that will show n pi star transition, because pi star antibonding pi antibonding molecular orbital is there, because all the elements are or atoms are joined by sigma bond, single bond. So sigma bonding and associated with sigma antibonding will be there. No pi bond, but due to presence of lone pair of electrons over oxygen in case of alcohol or amine, whatever may be. So there will be n pi star transition, which requires lesser energy. But this energy is not sufficient so that it will be in visible region. Visible is having lesser energy than UV, but it is not in visible region. We'll discuss that one. That's why alcohols, they are colorless. They observe, but they are colorless because they observe in UV region. Next transition is the pi pi star. That means which are having double bond. If pi bond will be there associated with pi bond, you have the pi antibonding molecular orbital also. So those compounds will observe, or you will, will observe in UV visible region, and there will be pi pi star transition. Though it is having lesser energy, so they will observe at higher wavelength. And finally, the lesser energy is n pi star transition. You have pi bond and also lone pair, as in case of carbonyl, C double bond O, acetone, ketones, aldehydes, they will have n pi star transition. So they will absorb at lower energy. But whether they looks colored or they are colorless, there is a concept that is known as chromophore and oxochrome concept. So that we'll discuss. Now you can see here the bonding as a energy difference is shown here. What I have discussed: sigma sigma transition in case of alkane. Okay, n pi star transition in case of alcohol, or in case of halo alkanes, because halogen contains lone pair of electrons. See, they are observing where 170, 167 millimicron, or methyl alcohol what 74 nanometer or micro millimicron and nanometer, same thing. Methyl chloride at 169 millimicron. All are in far UV, not coming under visible. Visible starts from 360 or nearly 400 millimicron. So they all are in UV region. Pi-pi-star transition in case of alkyne also. Then n-pi star in case of carbonyl compounds. Already told. Then moving to allowed forbidden transition, already discussed in the chromophore concept and oxochrome concept. Chromophore is defined as the any isolated covalent bonded group that shows a characteristic absorption in the ultraviolet or visible region. Ultraviolet or visible region, that is covalently bonded group. The group is responsible to absorb the characteristic light radiation, whether it is UV or visible. So the absorption occurs irrespective of the fact whether color is produced or not, because they will absorb in UV region. So color will not be produced because our eye can detect the visible region only. So chromophores in which group contain pi electron, they undergo n-pi star transition, such as ethylene or acetylene. Sorry, they undergo pi star. There is a mistake. The book is also here. They have not corrected this one. They undergo in pi star transition, not n-pi star. Chromophores which contain pi electrons and non-bonding electrons, they undergo n-pi star, pi star and n-pi star. This one, one pi will be n. You have to correct this one. Here they undergo pi star transition, where I have kept the cursor. And here both have written pi star, one will be n-pi star. Examples are carbonyls, nitriles, azo compounds, nitro compounds, all these things are there. Now, chromophores are again of two types: dependent chromophore, independent chromophore. So the chromophore which itself gives the color, which will absorb, is the independent chromophore. But if two or more such chromophores will be there, then color will be enhanced. That is a dependent chromophore. Your carbonyl group is a dependent chromophore. You can see here the carbonyl group absorbs at 180. The molar extinction coefficient where it is maximum, that is the value 160 to 180. 160 at n pi star, sigma pi, sorry, pi pi star is 180. It is molar epsilon max is 18,000 or 10,000. So this is the actual the peak. But n pi star transition occurs 285, but epsilon max is 15, very low peak. So we cannot distinguish this one. So this is due to, you can see 285 is coming nearly towards the visible. So one carbonyl group will be there, it is colorless. But in case of biacetyl, CS3, C double bond, OC double bond, OCS3. So color is pale yellow because two carbonyl groups are conjugated with each other, so color is enhanced or color depends. So carbonyl group is a dependent chromophore. Similarly, the alkynyl group, alkynyl with C double bond C, that is also a dependent chromophore. In case of one duck C double bond C, it may be colorless alkene. If it is diene, it is colorless. That means in case of polyenes, diphenyl polyenes, C6H5, C double bond C let whole N, again C6H5, diphenyl polyene. So when N is 1, 2 or 3, the compound is colorless. If N equal to 4, that means 4 C double bond C groups are joined together, then pale yellow color develops. If it is 5 to 7, it will be yellow in color. 7 to 9 or 10, it will be violet in color. You see, it is depending. And more than 11 or 12, it will be black in color. So diene or this C double bond C is also a dependent chromophore. Others are independent chromophore. Nitro, carboxylic acid, azo, amide, these are the
Sir, do
chromophores.
we need to,
Then
pardon, sir?
oxochrome.
Pardon, sir?
Yes,
Sir, these values, do we
you
need to remember, or when during analysis will be going on, we can see the
and
table and we can mix and match? Or we need to remember
hi,
these values?
don't no need to remember. Something we have to remember some people things. Let in case of potassium permanganate, it absorbs at 480. That we have to just when you will come across, then it will be there in your mind, but no need to remember. Some people,
Okay, sir.
typical groups are there. That we have to remember, but all we don't have to remember. We can't remember also. This is for discussion. I am showing. We can't remember all these things. Then oxochrome. Oxochrome, it can be defined as the group which does not itself act as a chromophore, but whose presence brings about a shift of absorption band towards the red or red end of the spectrum. That means longer wavelength. That means oxochrome, if chromophore will not be there, oxochrome will not give you the color. But in presence of a chromophore, if oxochrome will be there, then the color intensity will be enhanced or color will depend. Example you can see here. See, uh, no, it's not there. Where is nitro benzene and nitroaniline? It's there. Okay, anyway. So aniline, amine group is the chromophore. So this it absorbs at 280. But you see, when this lone pair of electron that is bound with H plus, giving the anilinium ion. So now lone pair is not there. So what happens? The n pi star transition is not there because n pi star transition requires lesser energy. So what happens? The absorption maximum, it it will now move towards the higher energy or lower wavelength. So which was 280 nanometer, now it becomes 254. Okay, so in case of this one, you can see the azobenzene and para-ethoxy azobenzene. So in case of azobenzene trans case, lambda max is 320 nanometer, but this oxochrome when it is present, now it changes to 385, increases. So the oxochrome, that is ethoxy group, is the oxochrome which increases the lambda max value. So why? Because the oxochrome, it participates in resonance or conjugation. Due to this conjugation effect, the energy decreases or wavelength increases. So now, so if these things happen, the absorption intensity, it may shift towards higher wavelength or towards lower wavelength, or it may shift towards maximum epsilon maximum. That means the absorption maximum may increase or decrease. So when the wavelength increases, that is known as the bathochromic shift, or it is known as red shift. The absorption maximum increases toward, changes towards or shifts towards the higher wavelength, that is red shift or bathochromic shift. When it shifts towards the lower wavelength, that is hypsochromic shift or blue shift. And if epsilon max increases, then it is hyperchromic. If it decreases, it is hypochromic. So four types of absorption shift will be there. This K band, R band not required. Go for now. The solvent effect, because solvent, as I told in the Lambert-Beer's law, solvent may form complex, so this law is not applicable. But when it is not forming the complex, the most suitable solvent, when the solvent will not absorb the UV or visible region, but a dilute solution of the sample is always prepared for the spectral analysis, and most commonly used solvents are ethanol. And ethanol is the best solvent, which is transparent down to 210 micrometer. So now when you are changing the solvent, so this is the upper wavelength limit where we can use these solvents. That means if our compound is not absorbing in this region, in this wavelength, then for that compound we will absorb the particular solvent. So that's for. So for ultraviolet spectroscopy, ethanol, water, and cyclohexane serves the as the better solvent. So these are the absorption range, transparency range of useful solvents. Effect of solvent, sorry, temperature and solvent no date. So now we'll go for conjugated dynes. How the absorption shifts. So you can see here, you have taken the example of butadiene, 1,3-butadiene, 2,3-dimethyl butadiene, and hexatriene. Hexatriene means again 3 double bonds are there. Here 2 3 dimethyl. Methyl is a substituent. So the lambda mass value increases as the conjugation increases. The conjugated dienes, the pi-pi side transition results in the formation of K band. So due to formation of K band, the lambda max value increases. So effect of conjugation, if conjugation effect will be more, then there will be more redshift. Wavelength will increase. This you can see the unconjugated alkene and conjugated diene. Unconjugated alkene, nothing is there. In case of conjugated diene, the absorption maximum is here. In case of trine, three double bonds are in conjugated with each other, then lambda max value still increases. So there will be redshift. So this effect of this conjugation, it can be found out by rule, that is Woodward-Fisher rule, for calculating the absorption maximum in dienes. This is in your syllabus, so we can go through this one. Longer the conjugated system, greater is the wavelength of absorption maximum. Okay, the intensity of absorption also increases with increase in the length of the chromophore. That is the conjugation. Okay. Okay, we'll have a break for 5 minutes, then we'll start.
Okay, sir.
Okay, start. Why others are not coming?
Yes, sir, we're here.
Oh, you are here. Only you two are here only.
Sir, mostly 4 to 6 only attending this.
Pardon? Hello?
Sir, yes, sir.
Oh, what you told?
Currently, last few days, this approximately 4 to 6 only attending like this only.
That's, okay, okay. Anyway, tomorrow I think we are expecting more. We will start. So the Woodward-Fisher rule for calculating the absorption maximum in dynes. So the rule is, as discussed here, you can see the alicyclic dynes or dynes contained in an open chain system where basic unit is butadiene. So that is one type of various types of double bond. Then second type is homoannular conjugated double bond. Homoannular, same thing is there, but conjugate double bond and conjugate double bonds are in the same ring. Okay, and here the conjugate double bond they are in the other ring. Heteroannular conjugate double bond. As you can see, so these three types are there, and other is there exocyclic. Exocyclic means one is out of the cycle. This is endocyclic, inside the cyclic. So exocyclic double bond is a double bond, part of conjugate system formed by any carbon atom of any ring but present outside the ring. So this is inside, so it is endo, this is exo. So this, if you consider two rings, you can see for it is exocyclic double bond to ring A. If you consider ring A, one cyclic, and this is the exo. Similarly, if it is this one, this is exocyclic. This is not exocyclic because it should be attached to the ring. In this case, two exocyclic. This one is exocyclic to ring B. This one is exocyclic to ring A. Just see the difference. Here, this double bond of B is exocyclic to ring A, but this is not the exocyclic because it is not attached to linked to the same ring. So this is not exocyclic double bond. This is exocyclic, but in this case, both are exocyclic to each other. Okay, so for this type of systems, Woodward formulate certain empirical rules for calculating the lambda max. Okay, and these rules are later on modified by Fisher. So according to these rules, each type of dyne has a certain fixed basic value. We have to fix the value, then we have to go on adding, then we will get the final absorption maximum where it will be absorbed. The same at let be 1 or 2 millimicron difference variation it will absorb. Theoretical and practical value will be nearly equal. You can see the number of alkyl substitution on the ring residue on the double bond, the number of double bonds which extend conjugation, and the presence of polar groups. So basing upon that, you can see this table value we have to remember, or it will be given, but some value we have to also remember. Parent value for butadiene system or a cyclic conjugated diene, it is 217. If it is triene, then it is 245. Homoannular conjugated, as we have discussed, homoannular conjugated means has the second one. This one, homoannular, this is alicyclic. For butadiene, you have to remember, for butadiene or diene, diene system or a cyclic conjugate diene, then it is 217. Acyclic triene 245. Homoannular it is 253, and heteroannular conjugate diene is 215. And then we'll go for increment. If alkyl substituent or ring residue, then 5 micro millimicron. Exocyclic double bond, we have to add 5 millimicron. Double bond extending conjugation 30. Oxochromes will be there. So if ether will be there 6. Then for thioether 30. Halogen 5 only. Secondary amine 60, and for acetoxy group 0. So now we'll give this example. You can see calculate the absorption maximum in the ultraviolet spectrum of 2,4-hexadiene. 2,4-hexadiene. You can see the structure of 2,4-hexadiene. So it is a diene. Basic value will be 217. Okay, and two alkyl substituents are there. So each having 5. We have to add. Okay, so 2 into 5, 10. So calculated value is 227 millimicron, and observed value is also found at 227. So the observed value and the calculated value for a particular compound, it can differ by only 5 millimicron. And for this compound, now let us see what is there. It is a butadiene system, you can say butadiene system. There are 2 alkyl substituents and 2 ring residue. This is one. 2 ring residues on the double bond. Moreover, there is an exocyclic double bond. So maximum basic value is butadiene system. So 217, 2 alkyl substituent, 2 into 5, 10, 2 ring residue, 2 into 5, 10, and 1 exocyclic double bond. So that is 5. So it is 242. Observed value also 242. And this one is heteroannular diene. So heteroannular diene, so basic value is 215. Heteroannular conjugated diene 215 as given in the table, and 4 ring residue 1, 2, 1, 2. So 4 ring residue, 4 into 5 equal to 20. So 235. Observed value is 234. For this is a homoannular conjugate diene, and there is how many? 3 ring residue. Moreover, it is contain an exocyclic double bond, because this is a cyclic, this is double bond. So exocyclic, everything we have to consider. This is first one, it is homoannular conjugated diene. This is cyclic system, exocyclic double bond is also there. Okay, 3 ring residue, 1, 2, 3. Here 2 and 3. So 3 ring residue. Okay, so 15, 253, 1 exocycle double bond 5, so 273. Observed value is 274. So like this, more examples are there. You can go through it. The Woodward-Fisher rule. Then distortion of the chromophore, it is not there. These polyenes I told, an example I have given, diphenyl polyene. See, when n equal to 3, 275 as I told is colorless. Now it is increasing, color is deepening. I told diphenyl polyene, this is different thing. In only the polyene is given, this residue is not given, substituent is not given. So this is the absorption. So as the number of double bonds in conjugate increases, the value of absorption maximum also increases. but does not increase proportionately as expected. It is probably due to the variation of bond length between double and single bond. So here you can consider, yes, this analog resonance led to uniform bond length. So we get this one. This is the alkyne type of thing. So with increase, the absorption maximum, lambda max is also increases. In case of lycopene, you can see conjugate system having methyl groups. So everything if you calculate, it is coming to 476 nanometer in the UV, sorry, in the visible region. So it is color. Okay, carotene, beta carotene is also colored due to for absorption at 453. This alpha beta, ultraviolet absorption in alpha beta unsaturated carbonyl compounds. In carbonyl compound, we have pi star transition and also n pi star transition. So generally, and we know the carbonyl compound is a dependent chromophore. So due to transition through HOMO to LUMO, it's high occupied molecular orbital to lower unoccupied molecular orbital. N pi star transition and pi pi star transition. So it is very intense and correspond to shorter wavelength. The first transition, pi pi star. The second transition, n pi star, involves the promotion of one non-bonding paired electron to pi star orbital. So in this case, the transition occurs with wavelength region from visible region. So it increases if conjugation increases, this will increases, and that also find out by the rule, that is the Woodward-Fisher rule. So in case of carbonyl, alpha beta unsaturated carbonyl, you have to go for the rule. For each exocyclic double bond, you have to add 5. For each double bond endocyclic, you have to add also 5. And if alkyl substituent will be there at alpha position, then 10, beta position 12, gamma and delta position will be 18. For each double bond extending conjugation 30, homoannular conjugated diene 39. So this table, the chromophore, and what we have to add. So you can see here the basic value is the 215 is the basic value. Double bond CH-COX, the basic value is 15. The basic value of alpha beta unsaturated ketone is 215 millimicron. So you can calculate like this. Other examples are there also. These things you can go through. Okay, so rest things are also not there. Heterocyclic system, steric hindrance. You can go through. So up to this you have rest part is not there. Compounds with NO bond is not there. Benzene at its derivatives, no. Condensed system is also not there. Fluorescence, phosphorescence is not there in the syllabus. Let me check. I think I have covered. Fisher-Woodard rule for conjugate diene carbonyl compounds. Yes. UV spectra of polyenes. Steric effect in biphenyls is also there. Fluorescent phosphorescence is not there. Okay, that much. Rest part is not there in syllabus. Okay, any doubt? We have covered the first one. Tomorrow we'll see the infrared spectroscopy. Okay, any doubt? See, you can go through the question. Charge transfer is not required. 67. So many examples are there, you can see. So here is one question you can see. Question number 25. Benzene is colorless. But isomer fullerene is yellow. So we compare benzene. Benzene is stabilized by resonance. Okay, but in case of fullerene, there is alternate double bond or it is a conjugate system, but resonance does not occur in this case because this is a pentadiene system having again extended conjugation. So therefore, it is a conjugate system. But in case of benzene, benzene is though it is they are having alternate double bond, but it is not a conjugate system that is stabilized by resonance. So therefore, it will not absorb or it will absorb at lower wavelength than fullerene. Fullerene is a conjugate system, cyclic system having also extended conjugation. You can see the pentadiene system having extended conjugation here. So that's why it will absorb in the visible region and it looks colored. Same thing, orthonitroacetanilide is deep yellow, but paranitroacetanilide is yellow. Why is the color of orthoisomer is different? So because the orthoisomer exhibits the intramolecular hydrogen bonding, while in the paraisomer, the intermolecular hydrogen bonding occurs. So internal or intramolecular hydrogen bonding stabilizes the excited state of the molecule to the greater extent than intermolecular hydrogen bond. See here. So therefore, the orthonitrosinolide is deep yellow. Another is the indigo, indigo tin dark. Why indigo tin is dark blue in color? Indigo tin is the transform is this one. So there will be hydrogen bonding. So the transform of indigo tin can be written like this. So the resonating structure is 2, which is more stable in the excited state. Also, the internal hydrogen bonding gives further stability in the excited state. Thus, the transition from HOMO to LUMO is very low. So therefore, it is dark blue in color. So these are some compound questions which can go through it. Further reading.
Sir,
Yes.
sir, this
Hello.
material is not available in e-Gyano course. So please you can share this material.
Yes, I will. I will share this one to you. I know it is not available.
Sir, sir.
Okay.
Thank you, sir.
Yeah. Just make a call to me so that I let
Sir, sir.
others. I don't know that. Okay.
Sir, you are added in the group of previously in practical classes.
Same group.
Sir, sir.
But here, Sucheta is there or not
Yes, sir,
Um,
I'm there.
in that group?
No, sir. No, sir.
Uh, you discuss. You go- or if anybody is not there, you just add it. Just add or join there so that I can share. Na?
sir,
You can talk with each other so that in the same group I will share all these things. Otherwise, if you are not in the group, then individual I can send to you. Just contact me.
okay, sir, sir.
Sir, for another
Okay.
subject, we were collecting and we were, I mean, you are in contact with you. I think Abhika is in contact with me, so I was forwarding them, and few others are with me, so I was forwarding them. Like that, we are doing.
Oh,
Or if they are
oh,
getting, then
okay.
they are
Okay.
forwarding. Okay.
Which one? Other
Sir?
subjects. Other
Other
subjects or what?
subject, yes, sir. Another sir, I forgot sir's name. Dr. Deep from this Ravensa College,
Okay. Okay. Okay.
polymer.
Okay. Okay. Anyway, I'll share it with you.
Okay, sir.
So okay. Today we'll stop here. Thank you.
Okay, thank you, sir.
Thank you.
Thank you.